Hi, in this video, we're going to look at an example of an explosion problem involving the conservation of momentum. So let's get started. Alex, who's 50 kilograms, and Bella, who's 40 kilograms, are astronauts working in outer space. They test out the conservation of momentum by holding each other's arms at rest and then lightly pushing off each other. Bella moves 3.0 meters per second to the right. What is Alex's velocity? So I've drawn a picture, and for these kinds of problems with momentum conservation, you always need to draw a before and after picture so you can define which direction is positive, which direction is negative. Also, it just helps to have a visual of what's going on so you can know how many objects you're starting with and how many that you're ending with. So in this case, we're starting with kind of one object. They're kind of lumped together into one solid object here, and then they break apart into two. That's why we call this kind of problem an explosion problem, even though there's not really anything explosive about what's happening here. But it's one object breaking up into two, essentially. You can think about it that way. So as long as there's no outside forces, we're in outer space here. These two they make up an isolated system. There are two objects that together, there are no external forces, outside forces acting on them. And so we can say that momentum is conserved in this example. That means that the total initial momentum, total Pi, should equal the total final momentum. Now, in this case, the total initial momentum, if you added up the momentum of both Alex and Bella, they're kind of together, so they have the same momentum, and it says that they're at rest at the beginning. And so the total initial momentum is simply just zero. Their total final momentum is just going to be the mass times velocity of each person. And so we have Alex and Bella, so I'm going to use A and B. So the mass of Alex times the velocity of Alex plus the mass of Bella times the velocity of Bella. Now we do need to keep this zero equals part because they're not, we're going to see later that as we work out this problem, we're going to need to do some subtraction. Let's go ahead and substitute in the numbers that we know. And so I'm going to put the mass of Alex as 50 kilograms. And the velocity of Alex is unknown, so I'm going to leave that as VA, plus the mass of Bella, which is 40 kilograms, times the velocity of Bella, which is 3 meters per second. And that's equal to 0. So 40 times 3, that's going to be 70 kilograms times meters per second. And that's added to this 50 kilograms times Alex's velocity. So now I'm going to subtract, hold on, keep it green, so I need to write the 0 equals here. Now I'm going to subtract both sides. I'm going to be solving for my velocity of Alex, so I'm going to subtract both sides of the equation by 70 kilograms times meters per second. Okay, and that's going to get me negative 70 on the left. And I'm going to have 50 times Alex's velocity, 50 kilograms times Alex's velocity here. So I'm going to divide both sides by 50 kilograms. Okay, so negative 70 divided by 50, I'll put that into my calculator. 70 divided by 50 is 1.4. So that's going to be negative 1.4. And if you look at the units, we have kilograms times meters per second divided by kilograms. So the kilograms cancel each other out here, and we're left with just meters per second for the velocity of Alex. So Alex moves to the left at 1.4 meters per second. So if I went back up here and labeled that, that's going to be 1.4 meters per second, whereas Bella moves 3.0 meters per second to the right. And I say to the left, negative means to the left here. He's moving at a lower velocity, like a lower speed, but he's also more massive. So they actually have equal momenta, but one is in the left direction and one is in the right direction. So That's all I've got for you in this video. Remember, how you do anything is how you do everything.